Okay, so first of all, as you can see, this note is quite long. So this would probably take us 3 in-school days. So be patient with yourself, and pause the video as necessary. The first lesson about organic chemistry is so long because it is really unique. Okay, so in the last few sections have all been about equilibrium and math, and this is really going away from that. If you took grade 12 biology, you would have started with biochemistry, and you would have talked about classes of organic molecules, how to recognize their functional groups. So yes, we're going to do that a little bit, but we're also going to switch and sort of focus more on how do you name those structures and their properties. Okay, so it's important to review the properties of carbon. So carbon can, I don't know what's going on there. Has 4 valence electrons, which means that it can form 4 covalent bonds. And if you remember, this Vesper shape is called tetrahedral. And the only reason why I'm reviewing that is because when you do your assignment and you look up your molecule, then you might see triangles like this, which means, if you remember, coming out of in a 3D way, and then these dotted lines mean coming into. But for our purposes, when we are doing organic chemistry, that doesn't really necessarily matter. The thing that does matter is that you can make 4 covalent bonds. So carbon must have 4 covalent bonds, and carbon is unique because it can bond to itself with single, double, or triple bonds, and it can also bond to other molecules, single, double, or triple bonds. So a lot of versatility. So when we first talk about the periodic table and counting the columns and looking at how many valence electrons something has, we skip the carbon column, right? And one of the reasons is we're only going to scratch the surface here of organic chemistry. You could take probably almost entire degrees in organic chemistry. Okay? So we're just scratching the surface. So when you have a single covalent bond, that means 1 pair of electrons is being shared. Like I said, you can do carbon atoms. It can do carbon to oxygen. We're going to see carbon to nitrogen. All of those mean that 1 pair of electrons is being shared. These are covalent compounds. And so when you have only single bonds, then we call the molecule saturated. Saturated because carbon is bonded to the maximum number of atoms, which is 4, and no more bonding can occur. So you'll see a little bit later that you can change. You can break double and triple bonds into single bonds, whereas once you get to single bonds, then the single bonds are a little bit tougher to break. So I had an organic chemist years ago. He's from Apotex, which is a pharmaceutical company sort of near Assumption in Brantford. And he said that sometimes he would set up reactions and 14 hours later, he would come back and get the results. So organic molecules in general, unless you're burning them like combustion, are not always super, super reactive, okay, when they have single bonds to break. Okay, so there you go. Single bond is a strong covalent bond. I feel like, what's happening here? There we go. Sorry. I don't know why. Okay. I don't know why it's jumping. Sorry. Carbon can join with 4 other atoms. So it can make double, single, triple bonds. And actually, we're going to look at rings or cyclic bonds. So again, something like this. And again, if you took biology, you would have looked at like cholesterol and stuff, had these rings in it, which means that carbon can bond with no beginning and no end, like not a chain in the molecule as well. So then this big note is focused on just carbon and hydrogen bonded together. And then we'll look at other functional groups, and then we'll get different families. Alcohols and ethers, aldehydes and ketones, carboxylic acids and esters, and amines and amides. What is going on? 3, 5. I think think this is where we are. We already did 4, not 7, not 6, 5. Okay. So double and triple bonds, now you have 2 or 3 pairs of electrons being shared. We did talk about that in grade 11. We just didn't talk about necessarily carbon, the diatomic molecules or things like that had double and triple bonds. And when they have double and triple bonds, they are said to be unsaturated. So they are not saturated with the maximum number of atoms. You can break the double and triple bonds and you can change it into single bonds. You've also heard these words again in biology. So an unsaturated fat means that there are at least one double or triple bond in the fatty acid, which makes the molecule unable to lay flat. So they have a kink in them, which means they don't lay flat, which makes them oils at room temperature because they can't form London dispersion forces, which means they don't form fats in your arteries or fats like salad dressings, like oils. So they are a little bit better. They don't sit as fat in your arteries and can cause heart attacks. Whereas saturated fatty acids, where it's all single bonds, they can lie nice and flat together and make a more solid-like substance, like saturated fats. Okay, so a carbon triple bond or single bond is difficult to break. And so these sites in organic molecules are not as reactive. So what we're going to see is when we talk about the reactions and the different families, then you're going to look for where the functional group is. So if it's connected to a oxygen or nitrogen, then that's much more reactive than just connected to another carbon. And except for burning is any organic molecule will burn. Double and triple bonds are more reactive because they aren't as strong, so they can be added, and the reaction's literally called an addition reaction, and these bonds are able to break. So polarity, we're also going to look at the properties. So, hold on, there we go. When you start to add other atoms to the chain, then you can influence the melting and boiling point and the solubility and the reactivity. So as we go through each family, that's what we're going to talk about. So the properties are determined by intermolecular forces because these are all covalent molecules. So does it hydrogen bond? Is it polar, have dipole, or is it just London dispersion forces, which is nonpolar? And organic molecules can actually have a nonpolar portion and a polar portion as well. We're going to talk about the length of the chain and that kind of thing. Now, along with this lesson, there is a reading from a different textbook that I think this explains polarity a little bit better, and then a worksheet. We would have taken the worksheet up together, but I will put those solutions there so you can check for yourself. And I never give read the textbook and copy in an answer, but that reading through that section and doing those questions, they go in order. You can do point form, will really help with the polarity part of this. So again, in first year, they don't necessarily do a lot of organic chemistry, like naming and reactions and stuff. However, even if you're in biology, you're going to talk again about properties and things like that. So doing that little extra reading will be really useful. Okay, so nonpolar occurs when there's an equal sharing of electrons in a covalent bond. So last year we spent a lot of time doing the calculating the change in electronegativity. Hopefully this year, because in organic, there's a variety in how the atoms are bonded. There's not a lot of variety in what kind of atoms there are. So really, if you see carbon bonds or carbon hydrogen bonds, then you can just consider those to be nonpolar. On the back of your periodic table, there is a table of electronegativity, but that's really a grade 11 expectation. So I'm not going to ask you to do that necessarily. And then if you have when carbon is bonded to a more electronegative atom, then the unequal pull of electrons creates a partial charge. So how will we know? So we're going to see OH, which is in alcohols. We're going to see NH in amines and amides. And then we'll see double bonded oxygen and single bonded oxygen as well. So really, you're looking for the presence of carbon connected to oxygen and or nitrogen, really, to be honest. So again, there's variety in how they're bonded together. There's really not a lot of variety in the types of atoms we're talking about. Okay, so if you see a section of a molecule that has oxygen bonded or nitrogen bonded, then that is a polar section of that molecule. So when you increase the polarity, then it increases the strength of the intermolecular attractions, as we've talked about before. So when you increase the strength of intermolecular attractions, then more force is required to break the bonds, which means an increase in melting and boiling points. So even in something, even if it's just dispersion, I use this example in grade 11 as well. So let's say you have methane, which is CH4, and something with more carbons. We'll talk about what this is. This is hexane or octane even, which is part of gasoline. That's 8 carbons. So if you have more than one molecule, which you always do, I'm just not including the hydrogens in the octane because it will get really messy fast. So then there's only one spot for dispersion forces to form. Here we have 8 spots. And there would be more, to be honest, but we'll just keep it simple. Okay, so the red dots are dispersion forces. Very simple model. Okay, so if you have more dispersion forces, then the molecule is held tightly together. So even though we say pump gas into your car, the gas we pump, the gasoline, is actually a liquid, right? And then the methane, this comes out of our Bunsen burner gas, which is a gas. It's a gas at room temp. Okay. So like I said, the presence of oxygen or nitrogen will allow for hydrogen bonding to occur between molecules, and that's the strongest kind of intermolecular force. So melting and boiling point are going to increase. And if a molecule is polar, we're also going to talk about solubility. Can it dissolve in water? And it's unfortunate that we can't do a lab because there really is a good lab where you would make your own organic molecules and you can look at the properties. Is it soluble? Is it insoluble? And one of the things with these molecules is if you think about gasoline, which is a big carbon chain, so carbon is nonpolar. It's hard because we think of solubility as like making a solid or a precipitate. But if you go and it's been raining, let's say, and you go to pump gas and there's a puddle, you can see the oil droplets. So sometimes that's called miscible. And so it's not that if it's not soluble, when we would have done the lab, it's not that you would have seen chunks of a solid, but you would have seen these oil droplets. Okay, so now we're looking at specifically hydrocarbons. So again, we're going to start simple and then we'll start to add stuff to the chain. So they contain carbon and hydrogen atoms only, which makes them nonpolar. Okay, so there are 2 types of hydrocarbons. There are aliphatic hydrocarbons, which is a much, much bigger group. So they can be single, double, triple bonded. They can be chains and rings. And then there's a separate group of aromatic hydrocarbons that have benzene. So on the next slide, I'll show you what benzene is. So really, this is a much smaller group. But one of the things one of the reasons they get their own section is because this benzene molecule is a very stable bonding arrangement. These double bonds don't break, which we'll talk about again. So this benzene molecule is, if the bonds don't break, then that means it's very persistent. So this molecule is a very, very toxic, powerful solvent. So let's say I opened a bottle of benzene in our classroom. It would make, it's so aromatic, like smelly, in not a good way, not like aromatherapy, that it would make everyone like vomit, like aspirate right away. You would get so sick just from the smell of it. So this is what this is called. This would be like an industrial solvent. So if you ever had to deal with something like this, you would have to wear like a full suit, almost like you're dealing with some kind of biological weapon, but it's just so toxic for your body that you would have to protect yourself from it. So things like paint thinner, they're what we call derivatives of benzene. So it's not just benzene. You can add stuff, substitute the hydrogens on the benzene ring. You just can't break the ring. So you think about, like, say you're gonna strip the paint off something. You can't do it in a closed garage. It would make you pass out, right? So even at a less toxic level, it's still really not good for you. Okay, so it gets, even though it's a small group, small number, and it has to have this benzene ring, then it's still, because of its properties, it still gets its own section. So these three here are all representations of benzene. This one is the lazy man's chemist, but you'll see this the most often way because the double bonds can be alternating, which means they can move around within the ring, which we call resonance. So again, you might have talked about that in biology. So we just use a circle. You don't have to worry about exactly where they are. So you'll most often see this ring, especially in your textbook. Okay, so when you are naming the organic molecules, and unfortunately there are many common names, and scientists eventually tried to move away from that because our world is getting smaller and they wanted a universal way to name these molecules. So IUPAC is International Union of Pure and Applied Chemists. So what they're saying is we want to, if we're in England doing work or in Chile or Argentina, we want to have the same system for naming these molecules. Okay, so the number one rule for organic chemistry is counting the longest carbon chain. So that's considered to be the root. And then the suffix is the ending, which is where we change the molecule's name based on what organic family it belongs to. Or we can add stuff to the chain, which we call a prefix. So this table of number of carbons is very, very important. Okay, so meth is 1 carbon, eth is 2, prop is 3, bute is 4, 5 is pent, hex is 6, hept is 7, oct is 8, and non is 9, and dec is 10. So if we were in class, I would encourage you, you would have to memorize those, okay, so that you would know, like when we count the chains, meth is 1 carbon, eth is 2, that kind of thing. Okay, so let's do aliphatic hydrocarbons first. So the simplest kind are called alkanes. They have only single bonds, and so they are relatively stable, and their ending is ane. Okay, so we're actually really not even going to worry about general formulas. We're going to draw the structures and name them a little bit differently. Okay, so the simplest one are straight chains. So let's say you had something like butane. So you would have to look on that chart. Bute means 4 carbons. Ane means single bonds. And they have to be joined together. So we need 4 carbons joined together. And then there's a variety of things that you can do. So carbon needs to have 4 bonds. So you can draw, the rest are considered to be hydrogen space fillers. So we just go in and make sure that carbon has 4 bonds. So the ones in the middle here have already 2 because they're bonded to carbons. So then they only need 2 hydrogens, whereas the ones at the end here have only 1 bond, so they need 3 hydrogens, okay? You can also do something like this, make the 4, and then just draw in ticks, because like I said, hydrogen's kind of considered to be a space filler. Your textbook, you can also use what's called condensed form, so like this. So this carbon at the end is CH3, then it's connected to CH2, CH2, and then CH3. Okay, you can draw it like that. And there's actually a stick way. So moving forward, if you choose to go to university and study chemistry, you might actually see this, which is a carbon is represented by each point. But if you don't like sticks, please don't feel like you have to, okay? So let's draw some more. So hexane. Again, 1, 2, 3, 4, 5, 6, and then go ahead and draw them in. Most people like this. Some people will like the sticks. Just go back and make sure. 1, 2, 3, 4, 5, 6. Okay. You could also find them like this, which is propane. But yeah, that's the big thing, is memorizing how many carbons are going to be in the longest chain. Okay, so wouldn't it be great if it could be that simple, but it's not. So we have, you can have branches. So what we're going to do, the first rule of organic chemistry is to count the longest chain. So that's going to be, right here it is. And then we also have to show where things are attached to the main chain. And we're going to use the lowest numbered carbon. That's rule number 2. So it's easiest to see really with an example. Okay, so I'll do one that's not too bad. Okay, so first of all, the annoying thing is we are used to counting from left. We're English readers, right? So we're used to counting from left to right. So just watch, don't write this down, okay? So you have to count the longest chain. So you can go 1, 2, 3, 4, okay? You could go 1, 2, 3, 4, and you can also go 1, 2, 3, 4. Okay, so you can count right to left, you can count left to right. You can, count a weird sort of little branch thing. They just have to all be connected. Okay, so what people find helpful to do is once they've decided what the parent chain is going to be, they just circle it. So no matter what way we count, this parent chain is going to be 4. So why not just use this one? And they circle it. And then you can see that there's a little branch coming off. So like this thing down here, right? That's coming off. So that's going to be our branch. So we'll worry about that in a second. So count the longest chain, our longest chain is butane. There are only single bonds. So that's called the parent chain, okay? Because it's the longest. All right, so now when there's a branch, we have to say, what is the branch? So the branch has 1 carbon. 1 carbon is meth, okay? And then so that's the number of carbons. And then when you name a branch, we don't want to use the same ending, so we use YL. Okay, so we have what the branch is, and then we're going to say where it is. on the parent chain. And this is where you have to do the lowest number. So if I use, let's say, the green way or the yellow way, my numbers, like counting from the left, then my branch is on carbon number 3. If I use the orange way or counting from the right, then my branch is on carbon number 2. So 2 is less than 3, so that's what I have to use. So the full name is 2-methyl. On carbon number 2, there's a methyl group, and then the parent chain goes at the end. Butane. I don't know what the little mark is, sorry. Okay, so yeah, this is a bit much, right? So unfortunately, the more practice you do, the better you will be at this. But I promise the assignment, which I'll make, it'll be a video after this, is so easy that it'll be okay. This is hard to do when you can't even ask me questions. Okay, so unless you email, which you can for sure. You can also add other things to a chain. You can add halogens, so chlorine becomes chloro, bromine becomes bromo, iodine becomes iodo. You can add NO2, which is nitro. We're not going to really worry about the priority list this year. So usually what we do, if you have more than one thing put on the chain, you put them in alphabetical order, prefixes. But even in class, if you didn't do alphabetical order, I wouldn't take marks off. Okay, so let's do another example. Okay, so this is huge and long and crazy, but let's just ignore that. But let's just, you know what I do? Start at the end. So hept is 7. Okay, now usually students like to draw better because you can decide which way you're going to count. And most people want to count from the left, right? They'll start here. 1, 2, 3, 4, 5, 6, 7. Okay, so now that I've decided that is number 1, then you can put things on accordingly. So tribromo means there are 3 bromines. So 5, bromine on the top, bromine on the bottom. It doesn't matter if you put them on the top and the bottom. This one you have to put one on each side because you have to. Chlorine has, carbon 2 has a chlorine, and then carbon 3 has an ethyl group. So ethyl means 2 carbons, eth is 2, and then the YL is a branch. So on carbon number 3, there are 2 carbons, and then at the end, always make sure carbon has 4 bonds. And usually students will just put in the ticks. Okay. So there are some structural isomers. Now, I left this actually filled in, but just in case you're looking at the homework or next year or whatever, like I said, there's not a lot of variety in the type of atom, but there is variety in how they're arranged. So these two molecules are C4H10, but you can see that the one has a branch and the one doesn't. So this would be butane, and this would be 2-methyl propane. So different molecules, they would have different properties, but the same type of atom. So sometimes you'll see these structural isomers attached to a parent chain, especially this one, isopropyl, like isopropanol, like rubbing alcohol. So it's connected, the branch is connected by its second carbon. So if you want to highlight all the R's, like this would be something else, like an octane or a benzene. You would have to have something else attached to it. And then sec-butyl would be this, it's attached by its second carbon. Tert-butyl kind of looks like a baby T. That's what those lines are. And then I-butyl or isobutyl kind of looks like a capital T. I don't know. It's not a perfect analogy, but just in case you see those, that's what that means. Okay. So alkanes are nonpolar. We already talked about that. They have weak intermolecular attractions, which are dispersion. More atoms in the molecules, the greater the intermolecular attraction. So boiling point and melting point will increase. So the, oops. So that means like the more carbons. So a longer chain, like we talked about methane versus octane. And then the single bond is not as strong, carbon-carbon single bonds are not as strong. They're not as reactive. However, they will burn. So you can do a combustion reaction. Oops. Okay. Any organic molecule will burn. All right, so cycloalkanes mean that they have rings, and all you have to do is put cyclo out front of their name. So it has to be above 3. Like you have to, the simplest one you can do is a triangle, a propane. The bigger they are, the more they will be stable. So if you remember from the first unit, we talked about buckyballs, like how big those carbon molecules could get because they were bigger pentagons and octagons in the structure, not tiny little triangles or squares like that. Okay. So I left these ones here. Most people, this would be cyclopentane. They use the stick version because it's just the shape, like each of these is a carbon. And then to draw in the hydrogens, as space fillers kind of becomes annoying. So this is cyclohexane. And then this would be cyclobutane. You can have them as branches as well, like say 2-cyclopropylhexane. So draw your hex, which is 6. And then on carbon number 2, there's a cyclopropyl, not just propyl this time, which means propyl is 3, which is a triangle. Okay, so now what happens if you have double bonds? Then we use the ending ENE. This is a different ending. Okay, so we're going to do the same rules. We're going to count the longest chain, and then this time we have to say where the double bond starts. So again, we're going to use the lowest number. So that's rule number 2. So we're going to do that again too. And then you can have more than one double bond as well. Okay, so I'll talk about that one in a second. Let's do this one. Sorry, it's supposed to be a C. Okay, so again, you count the longest chain. Now, the good news is with double and triple bonds, you'll want to include the double and triple bond as part of the chain. So this would be 1, this would be 2, this would be 3, and it doesn't matter. You can go down here and call this 4, but most people will just continue this way, 4. Okay, so now this is bute, but this time it's not it's not butane anymore. It's going to be butene. So we have to say that it's on carbon number 1. So it's kind of like a choo-choo train. Like you travel down the chain. The first carbon that has the double bond attached to it, that's the one what we say. So we don't say 2-butene. We say 1-butene. Okay, because on carbon number 1, that double bond is attached to it. So that can be a little bit tricky because the double bond's attached to 2 carbons, but we'll just do this one. 1-butene. And then on carbon number 3, there is a methyl. And then you can have rings. So this is cyclobutene. I forgot about over here. So you can call this 3-methyl-1-butene, or your textbook might use, or you might find it like this, but-1-ene, the one written beside the ending. So you might see that as well. Alkynes. Hold on, is there... I feel like there should be 31, 32, 33, no, 34. Okay. And then alkenes and alkynes are more reactive. So alkyne now is a triple bond. But again, we're going to follow the same rules. They are more reactive because they can be changed into single bonds. Whereas single bonds they could just be broken. That's it. So an alkyne, so this is 1-propyne. And then you could, this is rare, but just so I can show you the double ending. So we want to use the lowest number. So we're going to call this 1, 2, 3. So this is pent, but then we have to use the double ending. So on carbon 3, there's an ene, a double bond. And then carbon 1, there's a triple bond. Why did I order them ene first and then ine? Because they have, it's alphabetical order. If you put it in order of the number, I would not take marks off. Okay? Now, again, your assignment's going to be so easy, you know, don't stress too much about it. Okay, so again, we are, when you have aromatic hydrocarbons, when you have benzene, then the structure you're looking for, so this would be cyclohexane. It's not that. This is cyclohexene. It's not that. You either need to have alternating double bonds, like double bond, no double bond, double bond, or this ring. Usually they'll use the ring in the middle. That makes it benzene. So again, they are very smelly, and not in a good way, okay? So they're so stable. They will create resonance structures, like it can be the double bonds are spread out and the electrons are shared around the whole molecule, which makes a big deal. So then the double bonds do not break, which is unique. So you can have groups substituted on the ring. So this would be methylbenzene. So again, you've got the benzene ring, not broken, but the methyl group has been attached to it. And then you can also have double substitution. I left this filled in because, again, in case you see it, but I don't really want you to stress about it. Although the one back at the back here should have benzene. It got cut off, sorry. So, and unfortunately, because of organic, because they used to use really common names, then they use things like ortho, meta, and para instead of substitution at carbon 1 and carbon 2, carbon 1 and carbon 3, carbon 1 and carbon 4. But it really doesn't matter what way you do it. If you use the numbers, that's fine. But when you see these letters, that's what they're talking about. Okay? Oh, and phenol, don't memorize that. That's a common name. And then you can also substitute different things. So like bromine and chloro. So again, you could call that 1,4-bromochloro. Again, only because it's in alphabetical order. The thing with rings, same as cyclo, there's no beginning and no end. So technically this could be 1 and this could be 4, or this could be carbon 1 and this could be carbon 4. So it sort of is good because it doesn't really matter, but then that can be annoying to some people. Okay? Okay, so one more thing is that benzene could be added to a chain. So you could also have, let's say, 2-phenyl octane. So if benzene isn't the longest chain, so now octane is 6, then, 8, like an octagon. Okay, so then benzene is only 6. So then on carbon number 2, there is a benzene ring. But your textbook will also say benzyl as well. So you could see it either way. Okay, so that was a lot, and it's tough. I'm going to really take a look at this homework. So look at D2L and see which questions to answer, to try. And also I'm going to put that worksheet on there, which is good for properties too. Okay, so if you have any questions, we'll do our best online to try to get them answered. Okay, now the good news is most universities, if you choose to, like say you want to go to med school or something and you only have to take first year chemistry, they usually do very little organic. So that's more of like a advanced second year thing. So, I guess that's something to look forward to maybe, but it is hard in second year. So we really are just scratching the surface. Okay, thank you.